Hello friends, so today we are going to solve the questions from rotational motion and these questions are from the year 2024. We are going to solve two advanced questions from the year 2024 and from the year 2023 we are going to solve 16 mains question and for the same year there will be 4 advanced questions. So in totality we are going to solve 22 questions. Okay. And for this year 2023, specifically for this one, this is part 2. Okay. And for the year 2024, we have already done all this mains question. So this will be for the year 2024, this will be part 3. In the first two part, we only dealt with the mains question. Okay. So the first question, we are going to start with 2023 main and then we are going to move to 2023 advanced and then finally 2024 advanced. So in the first question, a solid sphere A is rotating about the axis PQ. If the radius of the sphere is 5 cm, then its radius of gyration about PQ will be square root of x centimeter. The value of x is. So basic sphere is given to us. We have sphere A. It is rotating about this PQ and we have to find out at a distance, the center distance of the sphere is 10 centimeter and the radius of the sphere is given as 5 centimeter. So we are supposed to find out the radius of gyration. So in order to find out the radius of gyration, first of all, we are going to find out the moment of inertia of this sphere A through the axis which is passing through the center. Okay. And we can call this as ICM will be equal to, let us suppose this is C and this point is of M. Okay. So 2 by 5 M R square. And then we are going to use parallel axis theorem and find out the moment of inertia about axis PQ. So let us suppose, let me write it first. We can say moment of inertia of sphere about the axis CM passing through its center. And we can, this is standard formula, ICM will be equal to 2 upon 5 MR square. Then we are going to use parallel axis theorem using parallel axis theorem, we can say moment of inertia about PQ, let us call this as IPQ, will be equal to ICM plus mr square, and r is the distance between the center of the sphere and the axis PQ. So we substitute the values and we can say that our IPQ will be equal to 2 by 5 mr square plus, let me call this a d, not, because it is much more easier to differentiate. This distance is d, mr square, and plus will be equal to md square. Therefore, radius of gyration we can write that our mk square will be equal to moment of inertia about axis PQ, and therefore we can write this as our mk square. IPQ is our 2 upon 5 mr square plus md square. This m cancels throughout, so we can now just substitute the values. We get this as 2.2 upon 5, radius is given to us as 5, plus distance is given to us at 10 centimeter, and we get this as our k square will be equal to 10 plus 100. Therefore, k is equal to square root of 110, and the radius of gyration is given as square root of x. So therefore, value of x is equal to 110. X is 110. Next question. It states that a uniform solid cylinder with radius r and length L has a moment of inertia I1 about the axis of the cylinder. A concentric solid cylinder of radius r prime, which is equal to r by 2, and length L prime equal to L by 2 is canned out of the original cylinder. If I2 is the moment of inertia of the carved out portion of the cylinder, then I1 upon I2 is. So we can say draw an approximate figure, and we are given a uniform cylinder, solid cylinder, suppose this is the axis and its radius is given as r and length is given as capital L. Okay. And in the second case, the cylinder is carved out from it, whose length is L prime and radius is our r prime. Relation between L prime and r prime with respect to the original radius is given to us. Okay, so we have to find out their moment of inertia. So we start with the standard formula, that moment of inertia of a solid cylinder, moment of inertia of solid cylinder, suppose that is I, will be equal to 1 by 2 mr square, and here m is the mass of the original cylinder. So we can say that mass of the original cylinder, or we can say we can find mass of the original cylinder, and suppose that mass is given as capital L, and this will be equal to our density multiplied by volume. Therefore we can say our mass M will be equal to, this is our density is rho multiplied by volume, volume will be our pi r square L. Therefore moment of inertia of original cylinder, or we can say original moment of inertia, original moment of inertia, which in this question is given as I1, will be equal to our half m r square. We substitute the m, we get this as our half m is rho pi r square L and multiply by r square. So we get that of I1 will be equal to half rho pi L R4. So this is the moment of inertia of our original cylinder. Okay. Now we are going to find out the mass of the carved out portion. Mass of the carved out portion, and let us suppose that mass is given as m prime. So we can write that our m prime density will be same and multiply by volume prime. Volume is going to change, density of the material is going to remain same. So we can say this will be equal to our rho, this is pi, and we have this is so this comes as pi r prime square, and we have this as L prime, and we can write this will be equal to our rho pi, and it will be our r by 2, and we have this as L by 2. Therefore our m prime, that the mass of the carved out portion, will be equal to, this will be our rho pi r square L, and this whole multiply by 1 by 8, and this is nothing but our original mass. Therefore we can say our m prime is equal to m divided by 8. Now we are going to find out the moment of inertia of the carved out cylinder. Moment of inertia of carved out cylinder, which is as of I2 will be equal to our 1 by 2 m prime r prime and whole square. So we already know a relationship between m prime and m and r prime and r. So we substitute them, we get our I2 will be equal to 1 by 2, this comes as m by 8, and we have this as r by 2 whole square. This comes as our m r square upon 64. And we can also modify it, or rather we can say write this as 1 by 2 m r square and 1 upon 32, and this particular is our, one second, yeah, so this was our half m r square. So this is our I1, so we here simply substitute our I1. So we get that our I2 is equal to our I1 multiplied by 1 upon 32. So the ratio I1 upon I2 is equal to 32. So answer is 32. Next question. It states that a car is moving with a constant speed 20 meters per second in a circular horizontal track of radius 40 meters. A bob is suspended from the roof of the car by a massless string. The angle made by the string with the vertical will be. So the car is traveling along a curved path, and let us suppose this is the original position of the pendulum, and as it is going to, car is going to turn, the pendulum is going to have a position which will be something like this. Let us suppose this angle is theta, and under this condition you can say in the downward direction we are going to have our mg, and there will be tension T along it, and we can divide this tension T into two components. So this angle will be theta, so we are going to have T cos of theta, and this will be over T sine of theta, and there will be over a centripetal acceleration which is our mv square upon r. So let's balance the forces. So we can say that the vertical component gives us T cos of theta is equal to mg, and horizontal component this will be giving us T T sine of theta will be equal to mv square upon r. So we can just divide them, and let us say this is 1 and 2. So from equation 1 and 2, from 1 and 2, we can write that as our T sine of theta divided by T cos of theta will be equal to our mv square upon r, and this is our mg. This t, m and m cancels out, and this gives us tangent of theta will be equal to v square divided by rg. And velocity is given as 20 and radius is 40, g is 10. So we substitute, we get this as 20 square 40 multiplied by 10, which comes as 400 divided by 400. This goes away, is equal to 1. Therefore theta is equal to pi by 4. So angle with the vertical is pi by 4. Okay, option number 3 is correct. Option 3 is correct. Next question. It states that an object of mass 8 kg is hanging from one end of a uniform rod CD of mass 2 kg and length 1 meter, pivoted at its end C on the vertical ball as shown in figure C. As shown in the figure, it is supported by a cable AB such that the system is in equilibrium. The tension in the cable is, take G as 10. So basic figure is given to us. We are having a infrared which is a CD, and at the one end, that is D, 8 kg mass is hanging, and this entire system is balanced by a string, that is our AB. Okay, we have to find out the tension in this cable. So we can just find out, or you can say draw the forces. So this point is C and this point is D, and in the downward direction here the force will be acting will be equal to mg, and point B, which is somewhere here, and it is connected to the string. Suppose the string is having a tension T and it is making angle of 30. Now we can divide this tension into components. So this component will be over T sine of 30, and other component will be T cos of 30. And there will be a downward force that will be act on this rod CD, that will be acting at its center of mass. So we can approximate it. Suppose this is the center of mass for the rod, and that is our mg. Okay, let me write this as m1g, and this will be over m2g. Okay, and the total length is given to us as total length is given to us as 100. So this will be our center of mass. So this is our center of mass, and it will be over 50. And so we are going to find out, because everything is in equilibrium, so we are going to find out the torque about point C. Torque about point C. So in the upward direction, we are only having one force, that is T sine of 30, and it is at a distance of 60 from point C. So this is our 60 centimeter. Therefore, we can write this will be equal to our T sine of 30, that is a force, multiplied by the perpendicular distance, that is our 60, will be equal to, in the downward direction we have two forces, M1G and M2G. Okay. So first one will be over M1G, and it is at a distance of 100, plus second one will be over M2G, and that is a distance of 50. So we can write this will be over T by 2 multiplied by 60 is equal to, our M1 is over 8. One second, yeah, M1 is over 8 into 10 multiplied by 100, plus M2 is over 20 multiplied by 10, sorry, it is 20 or 2 kg, not 20, and multiplied by 50. So we can say that here this goes by 30, so we get this as 30T will be equal to, and we will getting this as our 8000 plus, and this will be 20, and this will be 1000. Will be equal to 9000. Therefore, our T will be equal to 9000 divided by 30. So here 0 goes by 0, and this comes by 300. So therefore tension T is equal to 300 Newton. So tension in the cable is 300. Next question. It states that ICM is the moment of inertia of a circular disc about its axis CM, passing through its center and perpendicular to the plane of the disc. IAB is its moment of inertia about an axis AB, perpendicular to the plane, parallel to axis CM at a distance 2r by 3 from the center, where r is the radius of the disc. The ratio of IAB and ICM is x upon 9. The value of x is. So basic figure is given to us. We have a axis that is of CM. It passes through the center. Let us suppose this is O. And there is another axis AB, which is parallel to CM, but at a distance of 2 by 3 r. Okay. We have to find out their respective moment of inertia and find out the ratio. So first of all, we are going to take main axis and write the formula for our center of mass, and that is our standard formula. Okay. So we can say that moment of inertia of circular disc about its central axis about axis CM, which is given to us as ICM, will be equal to 1 by 2 mr square. And we can use parallel axis theorem. Parallel axis theorem gives us moment of inertia about axis AB will be equal to our ICM plus mass and distance square. Here distance between the two axes is 2 by 3. Okay. So we substitute and we get this as our IAB will be equal to ICM is our 1 by 2 mr square plus mass is our mass and distance is our 2 by 3 r whole square. And we can take our mr square as common, so we will be left with 1 by 2 plus 4 by 9, and this will be our, so we can say our IAB will be equal to LCM will be our 18, and this is our 9 plus 8 will be our 17 mr square. So we have both moment of inertia for CM axis and moment of inertia for our AB axis. We have to find out the ratio. Ratio gives us IAB and ICM. IAB is 17 upon 18 mr square. IAB is our ICM is our half mr square. Here mr square and mr square goes away, so we get this as 17 upon 18 multiplied by 2 by 1, and this 18 goes by 9, so we get this ratio will be equal to 17 upon 9, and in the question it is given as x upon 9, so we can say this is equal to x upon 9. Therefore value of x is our 17. So value of x is 17. Next question. It states that if a solid sphere of mass 5 kg and a disk of 4 kg have same radius, then the ratio of the moment of inertia of the disk about a tangent in its plane to the moment of inertia of the sphere about its tangent will be x upon 7. The value of x is. In this case, we have a solid sphere and disk, and both moment of inertia is about the tangent. So we can draw a rough diagram. So suppose this is our solid sphere, this is the tangent. Okay. And similarly, we have a disk, so this is a solid sphere. And this is a solid sphere. And then we are having a disk. Radius is same for both, and this is the, okay. So let us call this as our S prime, and let us call this as D prime. So first of all, we are going to find out the moment of inertia for our solid sphere or we can say, yes, moment of inertia for solid sphere for a axis which passes through its center. Okay. So let us call this as C prime, and similarly for here also let us call this as E prime. So this is our sphere and this is our disk. So you can say moment of inertia of solid sphere about its center. Moment of inertia of solid sphere about its center, about the axis, and this axis we called as C prime, and let us call that as our I, and this is our C prime, and for sphere that will be equal to 2 by 5 mass of the sphere and radius is r square. Now we are going to use parallel axis theorem and find out the moment of inertia about S prime. Parallel axis theorem, which gives us that moment of inertia about S prime will be equal to moment of inertia about the axis C prime for the sphere plus mass and distance square, and here the distance will be nothing but our radius. So we substitute and we get this as I S prime, SS prime will be equal to 2 by 5 ms r square plus ms and r square, and this comes as 7 upon 5 ms r square, and mass is given to us as a 5, so we substitute it, we get our ISS prime will be equal to 7.5 multiplied by 5 r square. This 5 and 5 goes away, so we get this as 7 r square. Same analysis we are going to do for our disk also. So you can say moment of inertia of the disk about the axis is called as E prime, which passes through the center is our E prime. So let us call this as E prime will be equal to 1 by 4 mass of the disk and our r square. And similarly for our parallel axis theorem, we get moment of inertia about D prime will be equal to, this is for our disk, let me this is I E prime and for disk, and we get this as I E prime for disk plus mass and d square. Therefore we get that our I d prime will be equal to 1 by 4 mass of the disk r square plus mass of the disk r square, and this comes as our 5/4 mass of the disk r square, and mass of the disk is given to us as 4. Therefore we can say the moment of inertia for the disk about the tangent, which is dd prime, will be equal to 5/4 multiplied by 4 times r square. 4 goes away, and this comes as 5r square. Now we are going to find out simply the ratio. So we can say that our ratio for our disk and for our sphere, that is our 5r square divided by 7r square. R square cancels out, and this comes as 5/7, and we are given that this is equal to our x/7. Therefore value of x is equal to 5. So value of x is 5. Next question. It states that a car is moving on a horizontal curved road with a radius of 50 meters. The approximate maximum speed of the car will be if friction between the tires and the road is 0.34. Take G as 10. So as the car is going to turn around the curved road, it will be the friction which is going to provide the necessary centripetal force. Okay. So we can say that our car moving along the curve friction provides centripetal force. That is, if the friction is represented as our Fr, or we can say this as F max, much more convenient, will be equal to our mass, velocity maximum square, and the radius. And in general, the formula for the friction we know is given as mu times the normal, and that will be equal to over mu times the mg. And we are interested in maximum velocity, so we can say our Vmax will be equal to our mass, and mass cancels out, so this comes as our mu rg, and its square root. Now we simply substitute the values, so we get our maximum velocity will be equal to square root of 0.34 into 10 into 10, and this comes as approximately as our 13 meter per second. So we get this will be our 13 meter per second. Next question. It states that a solid sphere of mass 2 kg is making pure rolling on a horizontal surface with kinetic energy 2240 joules. The velocity of the center of mass of the sphere will be. So it is a pure rolling motion, and it says that kinetic energy is given as 2240. So in case of pure rolling, we are going to have two types of motion, translational as well as rotational. So similarly, the kinetic energy will be translational kinetic energy as well as rotational kinetic energy. So we can say that our kinetic energy of rolling sphere let us suppose that is given as K, then this K will be equal to kinetic energy translational plus kinetic energy rotational. We simply substitute the respective formula, that is our half m v square plus half I omega square, and this is a solid sphere, so we know the moment of inertia. So we can say for solid sphere, moment of inertia, that is of I, is equal to 2 by 5 mr square. And for pure rolling, we also know that omega will be equal to v upon r. So we substitute all these respective things and we get that our kinetic energy K will be equal to half m v square plus half 2 by 5 mr square, and this comes as v upon r whole square. And here 2 and 2 cancel out, so we get this will be equal to our half mv square plus this r square, and this r square will be cancelling and this will be our square left. So this comes as our 1 by 5 mv square, and 10v will be the LCM, and this comes as 7 mv square. So from here, kinetic energy is given to us as 2240. So we can just substitute it. We have 2240 is equal to 7 upon 10, and mass is also given to us 2. The mass is about 2, so this comes as 2 and v square. So we can say that our v square will be equal to 2240 multiplied by 10, and this comes as 7 multiplied by 2. So our v square will be equal to our 1600, and v will be coming as 40 meter per second. Center will be 40 meter per second. Next question. It states that an object moves at a constant speed along a circular path in a horizontal plane with its center at origin. When the object is at x is equal to plus 2 meter, its velocity is minus 4 j unit vector. The object's velocity v and acceleration a at x is equal to minus 2 meter will be. So it is given that it is moving in a circular path with center at the origin. So we have a circular path with its center at the origin. So this is our origin, and at x is equal to 2 meter. So let us suppose this is our 2 meter. So this will be 2 comma 0, and other coordinate is our minus 2 comma 0. And the velocity is given as minus 4 j unit vector. So its velocity will be in downward direction, that is our minus 4 j unit vector. So it means it will be moving along this path, and at this point, let us call this point A, and at point B, which is at the other end of diagrammatically opposite end, its velocity will be in upward direction, okay, and that will be giving us plus 4 j unit vector. And okay, let's find out their velocity as well as our acceleration. So first of all, let's discuss a little bit about the acceleration. That is much more easier also, or we can say that we have to find out the acceleration at minus 2, and we can say at point A, there will be centripetal acceleration. Centripetal acceleration, which is, let us suppose, is our A. Therefore, we can say that our A will be equal to minus v square upon r, and we have this as I unit vector, okay, and its direction will be towards the origin along x-axis, toward origin along x-axis, and the magnitude of v is our 4. So therefore we can say that our acceleration A will be equal to v square, and radius is our 2, so this comes as our 2, giving us our acceleration is equal to 8 meter per second square. And this acceleration, please mind, it is at point A. Okay. And if I want to add a direction here, so direction will be along minus I unit vector towards the origin, okay, and now we come over to point B. At point B, our velocity, that is a v, in this case will be over plus 4 j unit vector, and acceleration will be equal to, magnitude will be same, that is about 8 meter per second square, and its direction will be plus I unit vector, okay, once again towards the center, so it will be plus I unit vector. Thus we can write the correct options. So we are having the velocity of plus 4j and the acceleration of plus 8I. So velocity is our 4j. Option number 2 is correct. Next question. It states that car is moving on a circular path of radius 600 meter such that the magnitude of the tangential acceleration and centripetal acceleration are equal. The time taken by the car to complete first quarter of the revolution, if it is moving with the initial speed of 54 km per hour, is t into 1 minus e raised to power minus pi by 2 seconds. The value of t is. So in this case, the car is moving a circular path. So this is somewhat a circular path, and it is saying in the first quarter. So let us divide into the quarter. And it is going to have two accelerations. One will be tangential acceleration, so this is our AT, and other one will be a centripetal acceleration. Let us call this as AC, and it is given that AT is equal to AC. So we are given that our tangential acceleration is equal to centripetal acceleration, or we can say that our A of t is equal to A of c, and we know that our A of c will be equal to v square upon r, and our A of t is equal to dv upon dt. And both are equal, therefore we can say that our dv upon dt is equal to v square upon r. Now it is a simple differential equation, we can solve it. So we can write this as dv upon v square is equal to dt upon r, and let's integrate it for 0 to v, and this comes as 0 to t. And okay, we are given initial speed, so it won't be 0. So let us suppose initial speed is our u. So we can say this will be equal to minus 1 upon v, and uv is equal to, this will be coming as t upon r, and from here we get that our t upon r is equal to 1 upon u minus 1 upon v, and it says that revolution, or we can say it is with respect to first quarter. Okay. So let us find out the length as well as our the length of the quarter circle first of all. So we can say the length of the arc length of the first quarter, arc length of first quarter, total, let us suppose that is given as s, total will be our 2 pi r and divided by 4. This comes as our pi r divided by 2, and with respect to our other way also we can write this as arc length, which is our s, will be equal to integration 0 to t v dt. And we already have our differential equation, that is our dv by dt is equal to vr square. So from here we can, let me write it here, So we have our dv upon dt is equal to v square upon r. From here we can write that our dt will be equal to r upon v square times dv. So let us substitute this is our in the integral form. So we get that our s is equal to 0 to t, and we are having this as v. Substitute value of dt is our r upon v square times dv. The square goes by the velocity. This will be equal to our we have to change the limits also, and the limit will be our from initial velocity v is equal to u and final velocity v is equal to our vf. So this comes as u vf, and we have this as our r dv upon v. So its integration will be our r natural log of v, and it will be upper limit vf minus natural log of u. So we get our s will be equal to r natural log of vf upon u, and our s is also equal to pi r upon 2. So this will be equal to pi r upon 2, and here this r and r cancel out. We get that our vf upon u will be equal to, this comes as e raised power pi by 2, and therefore our vf will be equal to u e raised power pi by 2. And we already derived the relationship between u, v and time t. So we are going to use this relationship, and we have 1 upon u minus 1 upon vf is equal to t upon r. So from here we can say that our t will be equal to r 1 upon u minus 1 upon vf, and let me write this as our vf, easy to differentiate. This is our vf. Which can be vf we already know. We get this as t is equal to our r. We are having 1 upon u minus 1 upon u e raised power pi by 2, and u 1 upon u we can take common. So this comes as r upon u is equal to 1 minus e raised power minus pi by 2, and we substitute value of r and u. We get that our t is equal to 600 upon 15, 1 minus e raised power minus pi by 2, and this comes as our 40, 1 minus e minus pi by 2, and the given equation is our t into okay, I forgot to change one thing, that it is given as 54 km per hour, and this is a meter and second. So I think I wrote it directly. Yeah. So we compare it with t t 1 minus e minus pi by 2. So this comparison gives us that the value of t is equal to 40 seconds. So value of t is our 40 seconds. Next question. It states that a thin uniform rod of length 2 meter, cross-sectional area A and density D is rotated about axis, passing through its center and perpendicular to the length with the angular velocity omega. If the value of omega in terms of its rotational kinetic energy E is alpha E divided by AD and its square root, then the value of alpha is. Okay. So in this case, it states that a thin rod and rotated about its axis which is passing through the center. Suppose this is our thin rod and we are having axis which passes through its center, and mass is m and L is the length. So we can say that moment of inertia of thin rod about its center perpendicular to length, and that moment of inertia is our I. So this I will be equal to 1 upon 12 ml square. And we can also find out the mass because density is given, and we can just also find out the volume. So we can say mass m will be equal to density multiplied by volume. Density is given to us as a d, volume will be equal to area multiplied by length. So length is 2 meter, therefore we can say our mass m will be equal to 280. So it means our moment of inertia I will be equal to over 1 upon 12. This is 2 times AD, and we have length L square. And we substitute value of L here also. So we get this as 1 upon 6 AD, and this comes as 4, giving us 2 by 3 A times D. And we are only interested in rotational kinetic energy. So you can say rotational kinetic energy, which is our E, is equal to half I omega square. Okay, so this is omega, and from here we can say that our omega square will be equal to 2 times E divided by I, and this comes as 2 times E, and we have this as 2 by 3 AD, which gives us this 2 and 2 cancels out, so we are left with 3 E upon AD. This means our omega is equal to square root of 3 E upon AD, and we are given that omega is equal to alpha E AD and its square root. Therefore, value of alpha will be equal to 3. So value of alpha is 3. Next question. It states that a uniform disk of mass 0.5 kg and its r is projected with a velocity 8 meter per second at t is equal to 0 on a rough horizontal surface. It starts off with a purely sliding motion at t is equal to 0. After t is equal to 2 seconds, it acquires pure rolling motion. See figure. The total kinetic energy of the disk after 2 seconds will be coefficient of friction, and G is given to us. And so at t is equal to 0, it is purely sliding motion. So this is our sliding, and at t is equal to 2 seconds, it is going to have pure rolling motion. So we have to find out total kinetic energy after 2 seconds. So we are going to start with our, we are going to find out the friction, and then we are going to find out the center linear acceleration, and then it is going to, because of friction, is going to produce a angular acceleration also. Okay. So we start with our acceleration due to friction. Acceleration due to friction. So first of all, we are going to have a kinetic friction. And let us suppose that is our F, which will be equal to mu times mg. We substitute the value, we have this as 0.3. Mass is our 0.5 multiplied by 10. So we have a kinetic friction, that is F will be equal to 1.5 newtons. And we can easily find out now linear acceleration of the center of mass. Linear acceleration of center of mass, which is our A, that will be equal to F upon m. F is our 1.5 and mass is our 0.5. So we get that our linear acceleration, that is our A, is equal to 3 meter per second square. So please keep in mind, this entire discussion is with respect to the frictional part. Okay, and there will be also the angular acceleration. So you can say angular acceleration, that is our alpha, will be equal to our F multiplied by radius divided by moment of inertia. And the standard formula for moment of inertia is our half m r square. So we get that of alpha will be equal to F times r, and this comes as a half m r square. The square goes with this r, and we get this as 2f divided by m times r, which will be equal to 2 times F is about 1.5, mass is about 0.5, and multiply by r. This will be coming as 6 upon r radian per second square. Now we come to the condition for pure rolling. Condition for pure rolling, and pure rolling we can write that our V is equal to omega times R, and here V is the velocity of the center of mass. So we can say that we can use the basic kinematic equation, that is velocity of center, which V will be equal to U minus AT, and U is about 18 minus A we found out is about 3, time is 2 seconds. Therefore we get that the V is equal to 12 meter per second. So this is our, and velocity after 2 seconds. Okay, so which means that here our velocity, which is our V, we found out is equal to 12 meter per second. So from here we can find out our angular speed. Angular speed, and this we have to make sure that we are calculating at t is equal to 2 seconds. So angular is our omega will be equal to alpha times t, and this comes as 6 upon r multiplied by 2, giving us 12 upon r radian per second. Okay. And we have to find out the kinetic energy at t is equal to 2 seconds. Kinetic energy at t is equal to 2 seconds, and at t is equal to 2 seconds there is pure rolling, and under the rolling condition we are going to have two types of, one is our translational and other one is our rotational. Therefore kinetic energy K will be equal to kinetic energy translational plus kinetic energy rotational, which comes as our half m v square plus half I omega square. And we substitute the values, we get this as our half, mass is our 0.5, and velocity we found is our 12 whole square, plus half, moment of inertia is our I omega square, and I is our not written. Okay, let me put it here. So this I will be equal to our half mr square, and omega will be equal to our v upon r whole square. So this we get as a half is equal to 0.5 into 12 whole square, plus this comes as 1 by 2 multiplied by 1 by 2, mass is 0.5, and r square cancels out, and we get this as our v square, which is equal to 12 square. Yes. Therefore we get that our total kinetic energy will be approximately equal to 18 joules. 1 second, not 18. Oh, 18, sorry. This will be giving us that our K will be equal to half mb square will be about 36 plus this is about 18, which comes as 54 joules. I think this was supposed to, yes, this comes as 54. Next question. It states that two discs of same mass and different radii are made of different materials such that their thickness are 1 centimeter and 0.5 centimeter respectively. The densities of material are in the ratio 3:5. The moment of inertia of the disc respectively about their diameter will be in the ratio x upon 6. The value of x is. So here the disc moment of inertia is with respect to their diameters. So we start from there only. We say that moment of inertia of disc about its diameter, and we can write that I diameter will be equal to 1 by 4 mr square. So we can write this formula for, because we are having two discs and they are made of different materials. Therefore we can write that our I d1 upon I d2 will be equal to 1 by 4 m1 r1 square 1 by 4 m2 r2 square. Here 1 by 4 and 1 by 4 cancels out, and this comes as m1 r1 square m2 r2 square. And they are having same mass. Okay. So we can say that same mass, our m1 is equal to m2, but their densities are different. So based on this we can write that our rho 1, okay, let me put it different way. We can say that our m1 will be equal to rho 1 multiplied by volume v1 is equal to rho 2 multiplied by volume v2, and we get from here rho 1 and our volume will be equal to pi r square h. Pi r square r1 h1 is equal to rho 2 pi r2 square, and we have this h2, and this pi and pi cancels out. So we get that our r1 square upon r2 square will be equal to rho 2 h2 rho 1 h1. Okay. And we are given that the ratio rho 1 by rho 2 is given as 3:5. So from here we can say our rho 2 upon rho 1 is equal to 5/3, and thickness is 1 and 0.5 centimeter. Okay, so we can say that our h1 is equal to 1 and h2 is equal to 0.5. Therefore h2 upon h1 will be over 0.5. So we can say that our r1 square upon r2 square is equal to 5 by 3 multiplied by 0.5. This gives us 5 by 6. And moment of inertia about the diameter is x upon 6. Okay, and we just wrote the relationship that their ratio, that is our id1 upon id2 is equal to m1 r1 square upon m2 r2 square. The mass are same, so it cancels out. So this comes as r1 upon r2 square, which is our 5 upon 6. And the ratio is given as x upon 6. So this is equal to x upon 6, giving us that the value of x is equal to 5. Value of x is 5. Next question. It states that a solid cylinder is released from rest from the top of an inclined plane of inclination 30 degree, length 60 centimeter. If the cylinder rolls without slipping, its speed upon reaching the bottom of the inclined plane is, basic figure is given to us. The length of inclined plane is of 60, and this is our cylinder. It is rolling without slipping, and angle of inclination is given to us at 30. So we can say that our we are having rolling without slipping. So which means that, let us suppose h is the height. So it starts from rest. So at this point we are going to have only the potential energy. So let us suppose this is point A and this is point B. So it is rolling without slipping, and let me start with conservation of energy. So we can say conservation of energy so which basically means that potential energy at A will be equal to kinetic energy at B, and potential energy at A will be equal to over mgh, and kinetic energy at B, as the motion is rolling without slipping, therefore our kinetic energy at B will be equal to our kinetic energy translational plus kinetic energy rotational. Translational is our, suppose velocity at point B is our v, and this comes as our half I omega square. and it is a solid cylinder. Therefore we can write that the value of I will be equal to over half m r square, and our omega will be equal to v upon r. So we can use the conservation part, and we can write that our mgh will be equal to half m v square plus half 1 by 2 mr square, and this comes as v square, and this r goes by r, so this will be coming as 1 by 4 mv square, and this is half mv square, and this will mass, okay, this will be giving us 4 will be our LCM, and 4, and we have our mv square, and this will be 2 plus 1, that is our 3, and this mass and mass cancels out. Therefore we get that our v square will be equal to 4 by 3 times gh, and our height h in terms of the length, let us suppose this length is L, so we can say h is equal to L sine of theta, which comes as 0.6 multiplied by 1 by 2, giving us 0.3 meters. So we get that our v square will be equal to 4 by 3, g is 10, and h is 0.3. So this gives us that the v is equal to 2 meter per second, is 2 meter per second. Next question. It states that moment of inertia of a disk of mass m and radius r about any of its diameter is mr square by 4. The moment of inertia of this disk about an axis normal to the disk and passing through a point on its edge will be m square x upon 2. The value of x is. So here we are having that we are having two, we can see axis. One is with respect to the diameter, and other is any point which passes through the edge. So we can just draw the approximate figure, and so suppose this is the center, and first axis is along the diameter, and suppose this is the axis along the diameter, and other one is normal to the disk passing through the point on its edge. Okay, so let us suppose this is the other one. So let us call this as our ix, and this x is our iy, and let me check once again. I think moment of inertia of disk mass m about any of diameter is mr square 4. Moment of inertia of this disk about an axis normal to the disk and passing to the point of edge is okay. So we have to use our suppose r is the radius, and okay, so in this case we are given that this I of y is mr square x by 2, and so let us draw an axis which is parallel to I of y. So this is the axis which passes through the center and is parallel to IY. Let us suppose this is center O and this axis is our CM. So in this case, this IX is perpendicular to our CM. And both these axes are the representation of the diameter. Okay, so this is also our diameter, and other axis is also passing through the diameter. Okay. So let us call this as diameter D1 and let us call this a diameter as D2. So we are going to use first of all perpendicular axis theorem, and we can say that moment of inertia about center perpendicular to the plane. Okay. And one second, this is my mistake. This I of y is perpendicular to the disk. Okay, moment of the disk normal to the disk. Okay, so we can assume that it is going normal into the plane. So we are going to find out an axis which is perpendicular to both D1 and D2 but parallel to this. Okay, that was my mistake. And let us delete this also. So in this case, let me, so moment of inertia about the center perpendicular to the plane, okay, which is our this axis. Let us call this as A1 axis and this we are calling as A2 axis. Okay, so it means A1 axis, and this A1 axis is perpendicular to both D1 as well as D2. Okay. So we can say that our I for A1, which we can also call as moment of inertia perpendicular at the center. Moment of inertia perpendicular at center, and from perpendicular theorem we can write this will be equal to over Ix plus Iy. Okay. And in this case this will be our Iy and this will be our Ix. Okay, so Ix is the representation of our D1 and Iy is the representation of our D2, okay, with respect to diameter. So we can say for disk our IA1 passing through center of mass. Let me rephrase this also. We have this is our center of mass and through our A1, and this is also our I center of mass through A1 is equal to our I with respect to diameter D1 plus I with respect to diameter D2, and diameter will be same, so we can say this will be equal to twice I, let us suppose, diameter D1. So we get this as I center of mass with respect to our A1 will be equal to twice, and with respect to diameter we have 1 upon 4 mr square, which gives us 1 by 2 mr square. And now we are going to use parallel axis theorem, because the axis A2 and A1 are parallel with each other. So we can say parallel axis theorem. We have our moment of inertia with respect to our edge, and point is our A2 will be equal to our ICM with respect to A1 plus mass and d square. Here d will be equal to radius, so we get this as our 1 by 2 mr square plus mr square. So we get that moment of inertia with respect to our edge through point A2 will be equal to, this comes as 3 by 2 mr square, and we are given that this is equal to x by 2 mr square. Therefore value of x is equal to 3. Value of x is equal to 3. Next question. Okay, so all the questions which we did previously were for the mains 2023. Now we start with the advance of 2023. It states that a bar of mass m 1 kg and length 0.2 meter is lying on a horizontal frictionless surface. One end of the bar is pivoted at a point about which it is free to rotate. A small mass m 0.1 kg is moving on the same horizontal surface with 5 meter per second speed on a path perpendicular to the bar. It hits the bar at a distance L by 2 from the pivoted end and returns back to the same path with velocity v. After this elastic collision, the bar rotates with angular velocity omega. Which of the following statement is correct? So we can just draw the basic diagram of our question. Suppose this is our rod and this is a pivot point, let us this is called O, and this is O prime, and we are having a mass m which strikes the rod at the midpoint. Okay, so this point will be distance L by 2 and this distance will be also over L by 2, and let us suppose the velocity with each strike is given as u. And after striking, the rod, which is our free to rotate about point O, is going to rotate in this direction with the angular velocity omega, and this mass m returns back with the velocity v. Okay, so this is the basic, you can say, diagram. And okay, so in this case we are going to use angular momentum conservation with respect to point O, that is a pivot point. So you can say angular momentum conservation about point O. Point O. And we are going to start with our moment of inertia about point O. Moment of inertia about point O, which is equal to I is equal to 1 by 3 ml square. So we are going to have two situations. One will be before collision, other one will be after collision. So we can say angular momentum before collision and the rod is stationary, only small mass m is moving. Therefore we can say that our L initial will be equal to mu, and this comes as L by 2. We substitute the values, we get mass is our 0.1, velocity is our 0.5, 0.1, giving us 0.05. And after collision, let us call this as our L final will be equal to rod is moving I omega plus our mass is also, that is a mv upon L by 2. So we get that our L final will be equal to I omega, that is our 1 by 3 into 1, and this is our 0.2 whole square omega plus 0.1, 0.1, and 1 second, length is 0.2. Yeah, my mistake, I am writing it as this is 0.2 divided by 2 and multiply by v. So we get that our L final will be equal to 0.04 divided by 3 times omega plus this is our 0.01 times v, and L initial is equal to L final. So we get this will be equal to 0.05, and we can write this will be equal to 0.0133 omega plus 0.01 V is equal to 0.05. Now we are going to use kinetic energy conservation because it is a elastic collision. So we can say that our elastic collision with respect to our kinetic energy, and we have kinetic energy after collision, will be equal to half I omega square plus half m v square. And before collision, will be equal to half m u square, and they will be equal with each other. Therefore we can say that our half I omega square plus half m v square is equal to our half m u square, and we can write this our half mass is our 0.1 and five square. This comes as 1.25, and we substitute value of our moment of inertia. That is our 1/3 ml square, or we can, this is also our moment of inertia, we can substitute it this also. So we get our 1/2 0.0133 mega square plus 1/2 mass is our 0.1 and v square is equal to 1.25. So we get this as 0.0066 omega square plus 0.05 v square is equal to 1.25, and we have two equations. This is equation number 1 and this is equation number 2. So from equation 1 and 2 we can solve for our omega as well as v. From equation 1 and 2 we can get that our value of v is equal to minus 4.3 meter per second, and our omega will be equal to 6.98 radian per second, and this is negative sign is only for the direction purpose. So this is 4.3 and 6.98. 4.3 and 6.98, so 4.3, option number A is correct. Option A is correct. Next question. was also asked the year 2023 advance, and it states that two point-like objects of masses 20 gram and 30 gram are fixed at two ends of a rigid massless rod of length 10 centimeter. This system is suspended vertically from a rigid ceiling using a thin wire attached to its center of mass as shown in the figure. The resulting torsional pendulum undergoes a small oscillations. The torsional constant of the wire is 1.2 10⁻⁸ Newton meter per radian. The angular frequency of oscillation is n into 10⁻³ radian per second. The value of n is, so basic figure is given to us, 30 gram and 20 gram, and it is rotating along this direction, okay, like a pendulum, and we are supposed to find out its frequency of oscillation. Okay. So here let us suppose we are having two masses. This is our M1 and this is our M2, and the distance is our x1, x2. Let me write it here, that our masses, we can say let x1 and x2 be the distance of M1 and M2 from center of mass along the rod. Therefore, we can find out, because so we can say that center of mass position from M1, okay, and M1, let us suppose this is our M1 and this is our M2. This distance is our x1 and this distance is our x2. So we are going to find out center of mass from M1. So we can write this as our xCm will be equal to our M2 times L divided by M1 plus M2, which comes as M2 is our, one second, this is our M2 and this is M1, x2 and x1. Okay. So we are having our M2 is 30 multiplied by the length, that is about 0.1 divided by 30 plus 20, which comes as 0.06 meters. Okay, so this is the center of mass with respect to M1. Now we can find out the distances of our center of mass. So we can say distance from center of mass, and that is our R1 will be equal to our xCm is equal to 0.06 meters and our R2 will be equal to L minus x cm, and L is our 0.1, this is 0.06, so we get our R2 is equal to 0.04 meters. Now moment of inertia about center of mass. Moment of inertia about center of mass, that is our I will be equal to m1 r1 square plus m2 r2 square. Okay, and so we get our I is equal to, this is our 0.02 multiply by 0.06 whole square plus our 0.03 and 0.04 whole square. So this, because let me one second. Okay, so we get that our I, moment of inertia about the center of mass, will be coming as 1.2 into 10 to the power minus 4 kg meter square. Now we can just find out our angular frequency. Angular frequency, that is our omega, is equal to square root of k upon I. This comes as 1.2 into 10 to the minus 4, and I is our 1.2 into 10 to the power minus 10 to the minus 8. Minus 4 and its square root, and this comes as 10 to the power minus 2, and we are given that our frequency omega is equal to n into 10 to the power minus 3, which will be equal to 10 to the power minus 2, and it can be written as 10 into 10 to the power minus 3. Therefore value of n is equal to 10. And this can be also done by using the double derivative with respect to angle theta. Answer will be coming same. Next question. It was also asked in the year 2023 advance, and it states that an annular disk of mass m, inner radius a, outer radius b, is placed on a horizontal surface with the coefficient of friction mu as shown in the figure. At some time, impulse j x unit vector j naught x unit vector is applied at the height h of the center of the disk. If h is equal to hm, then the disk rolls without slipping along the x-axis. Which of the following statement is or are correct? So here it is basically a rolling motion without slipping. Okay. And So let us discuss this rolling without slipping when impulse is applied. After impulse, so you can say that condition for pure rolling after impulse. And first is our linear momentum after impulse. After impulse, so we can say our mass into velocity of our center of mass will be equal to our I naught, and from here we can say that velocity of center of mass is equal to our I naught upon m. Then angular momentum about center of mass, and in this case we have to remember that the impulse is applied at a height h from the center. Disk rotates due to impulse at height h. So we can say our angular momentum, that is our L, will be equal to our ICM omega plus m VCM multiplied by h, and this will be equal to our I naught times h. Okay. And one second, this is our J naught, not I naught. J naught, and here also J naught. And we know that our moment of inertia for the annular disk, moment of inertia of annular disk, that is our ICM, will be equal to 1 by 2 m a square plus b square, and this impulse gives a angular velocity omega. So we can say that our impulse gives angular velocity omega about center of mass. Therefore we can say that I center of mass multiplied by omega is equal to our J naught times h. So from here omega will be equal to our impulse J naught h upon I CM, and we substitute our ICM, so this comes as J naught upon h upon m a square plus b square. Now it is rolling without slipping. So we have rolling without slipping. This gives us that the velocity of center of mass will be equal to radius b multiplied by omega, because the disk is rolling along x-axis with respect to radius b. Okay, so it is moving in x direction and radius is our b. So we can write that disk rolls along x-axis and our radius is our b. Therefore, we can write that our VCM is our J0 upon m is equal to b, and omega we just found out is our J0 upon h m a square plus b square. And from here we get that our h is equal to this J0, m and m cancels out. We get h is equal to it is 1 by 2. I missed somewhere 1 by 2. ICM is 2. Sorry, not 2 but 1 by 2. By 2. So this is m by 2, and here also 1 by 2. So we get this as 2b. H will be equal to a square plus b square divided by 2b. And because in the question it mentions that if h is equal to hm, okay, then only there is rolling without slipping. Okay, so we can just substitute h by hm. Therefore we can say that our hm is equal to a square plus b square divided by 2b. Now we are going to check all the options one by one. So we have option A. Option A states that our friction is not equal to 0, and it says that A tends to 0, then hm is equal to b by 2. So obviously when friction is not equal to 0, there will be a rolling motion, and we substitute A is equal to 0, and we get that our hm will be equal to, this comes as b square upon 2b, square goes by b, so we have hm is equal to b upon 2. So this is true. Now we come to our B option. B gives us that mu is not equal to 0 and A tends to B, and our hm will be equal to B. Same solution, we can write that our hm, A is our B, so this comes as our B square plus B square upon B upon 2B. This will be equal to our 2B square upon 2b, 2 and 2 square and square goes away, and this comes as a b. So this is also true. We have option C. Option C gives us that, so option A and option B are correct. So for h is equal to hm, initial angular velocity does not depend upon the inner radius A. So you can say for h is equal to hm, and we know that our angular velocity omega is equal to 2 j naught h upon m a square plus b square, and we know that our at h is equal to hm, which is equal to a square plus b square upon 2b. Therefore omega is equal to, this comes as 2 times j naught upon m a square plus b square, and this will be coming as our a square plus b square upon 2b, and this a square and a square plus b square cancels out, 2 and 2 goes away, so we get that our omega will be equal to our j naught upon mb. mb, so which is independent of A. So this is also true. And now we come to our D part. It states that mu 0 h 0 slides without rolling. Okay, mu 0 h 0. So it means mu 0 h is 0. So based on this we can say impulse will be applied at the center, because in the figure the impulse is being applied at a height h. If this height becomes 0, then impulse will be applied right at the center. Okay. So we can say that impulse is applied at the center. Okay, and also mu 0, so we can say no friction. If friction is absent, then we can say no torque. If there is no torque, our omega will be equal to 0. Therefore there will be slide and without rotation, because for rotation in general friction should be always present. So this D is also true. So this all the options A, B, C and D are correct. Next question. It states that a thin circular coin of mass 5 gram and radius 4/3 is initially in horizontal xy plane. The coin is tossed vertically up plus z direction by applying an impulse of pi/2 square root into 10⁻⁻² Newton second at a distance 2/3 centimeter from its center. The coin spins about its diameter and moves along plus z direction. By the time the coin reaches back to its initial position, it completes n rotations. The value of n is, so basic figure is given to us. So we have disc and this is the position of the coin. Impulse is applied to it and its move clips and it rotates about its diameter, okay, like a coin toss. So we have to find out the number of, you can say, rotations it is going to. So this is impulse. Let us suppose this impulse is represented as J. Okay. So first of all, we are going to find out the angular velocity of the coin. Angular velocity of coin. And in this case, this, one second, let me redraw the figure. There was small discrepancy in my interpretation. We have this is a circular coin, complete one, and impulse is applied at this position, and it is going to, you can say, with respect to diameter, it is going to move up in the z direction and it is going to rotate in this way. Okay. And we have to remember that impulse is applied off center by a distance of 2/3 centimeter. So you can say that the impulse applied off center, applied off center. So because of this off center, the torque generates spin about diameter. Torque generates spin about diameter. And we can write that our angular impulse will be equal to J multiplied by distance r, and that is equal to over I multiplied by omega. And the disc, this is a coin in the form of a disc, it is rotating about its diameter. So we can say that moment of inertia of thin disc about diameter. And our I will be equal to 1/4 mr square. So we can write that our Jr is equal to I omega, which is omega is equal to Jr upon I, giving us Jr. I is our 1/4 mr square. So we get our omega is equal to 4 Jr, and we have our mr and j is our square root of pi by 2. So we substitute them. This comes as 4 square root of pi by 2, and radius is given to us as 4 by 3 centimeter. No, sorry, radius r. This is r, small r, 2 by 3 centimeter. So this comes as 2 by 3. Mass is given to us as 0.005, and we have this as 4 by 3 whole square. Okay. And this is 2 by 3 centimeter, so this will be coming as 10 to the power minus 2, and here will be 10 to the power minus 4. So we get that our omega is approximately equal to 375.5 radian per second. And it moves, the impulse is also going to provide a linear velocity. Okay, it is going to rotate as well as move upward. So there will be two types of velocities. One will be angular velocity, other one will be a linear velocity. So let us analyze with respect to the linear velocity, and we can say the impulse gives linear velocity, and let us suppose that is our v naught. So this v naught will be equal to impulse divided by mass m, and this is our square root of pi by 2 divided by mass is 0.005. This comes as 2.5 meter per second. And let us suppose this is initial position of the coin, and this is the final position of the coin. Okay. And this total time it takes is, let us suppose, t. So, and it starts from the rest and moving with the velocity 2.5, that is our v naught. Therefore we can say that time, okay, so you can say time to go up and come down, let us suppose that is capital T, which will be equal to 2 times small t, or which will be equal to 2 v naught by g. So we get this as capital T will be equal to 2 v naught is our 2.5 and g is our 10. This comes approximately as 0.5012 seconds. Now we can easily find out number of rotations. Number of rotations, let us suppose that is our n will be equal to omega t divided by 2 pi, and sorry, this is capital T, because it is going to rotate going up as well as coming down also. Okay, so omega we found out is our 375.5 into 0.5012 divided by 2 multiplied by pi. So from here we get this value of n is approximately equal to 30. So value of n is 30. Next question. This was asked in the 2024. So up till now we have done mains and advanced question from year 2023. So we are going to start with 2024 advanced. The disk of mass m and radius r is free to rotate about its vertical axis is shown in the figure. A battery operated motor of negligible mass is fixed to this disk at a point on the circumference. Another disk of the same mass m and radius r by 2 is fixed to motor's thin shaft. Initially, both disks are at rest. The motor is switched on so that the smaller disk rotates at a uniform angular speed omega. If the angular speed at which the large disk rotates is omega by n, then the value of n is. So we are having two disks. Forget about the motor. One is a smaller one, other one is a bigger one. So mass of the same. Smaller one is r by 2 radius, and capital one is bigger one is having the radius r. Okay. So in this case, let us assume that we are having this is our bigger disk and this is our smaller disk. Okay. And this is center. Suppose this bigger disk move in this direction, then the smaller disk is going to move in opposite direction in order to conserve the momentum. And this is the center. Its mass is our m, radius r by 2, and its mass is our m and radius is our r. So let's find out our angular momentum. So we can say that contribution to angular momentum. Contribution to angular momentum. So we start with our large disk and large disk. Suppose this is our L large will be equal to moment of inertia of large disk, and we assume that it is moving with the angular velocity of omega prime. So this comes as multiplied by omega prime, and for moment of the moment of inertia for the disk is our half m r square multiplied by omega prime. And we have smaller disk. So it is rotating in its axis which is independent. Therefore we can say that angular momentum small and so this small disk is going to have two type of motion. One will be along its axis and other one will be you can say orbiting around the this larger disk. Okay, so it will be also moving in this direction. So small disk is going to spin as well as rotate. So small disk, so angular momentum of the small when it is spinning its own axis. So we can write this as our moment of inertia for the small and spin multiplied by omega, its angular velocity. Okay. It is moving with the angular velocity of omega. Therefore, we get that our angular momentum of small, which is spinning, will be equal to, this will be our half mass is m and radius is our r by 2 whole square multiplied by omega, which gives us 1 by 8 mr square times omega. Now this small disk is going to rotate about the, or we can say, orbital motion. So we can say that small disk orbital motion. And it is going to move about the larger radius, that is our r. So we can say that our moment of the small, and it is in orbital motion, will be equal to m r square and our omega prime. Now we can use conservation of angular momentum. Conservation of angular momentum. We have our momentum of the large plus momentum of our small, which is in orbital motion, minus momentum of our small, which is in spin, is equal to 0. So we can see that the rotation of the last disk and the orbital motion of a small disk is in same direction. Okay, that's why there is addition of both. So we simply substitute their respective equations. We get this as half mr square omega prime plus mr square omega prime minus 1 by 8 mr square is equal to 0. And here mr square, we can just take it out, and we get this equal to our 3 by 2 omega prime is equal to, here I forgot to mention omega, this is our 1/8 omega. So we get that our omega prime is equal to 1/12 times omega. So this gives us relationship between the velocities. And if the angular speed of larger is omega upon n, so angular speed of larger is omega upon n, and the larger is our omega prime. So we can say that we are given that omega prime is omega upon n. So making comparison, we can say that the value of n is equal to 12. Value of n is 12. Next question. It states that a thin uniform rod of length L and a certain mass is kept on a frictionless horizontal table with a massless string of length L. fixed to one end. Top view is shown in the figure. The other end of string is pivoted to a point O. If the horizontal impulse P is imparted to the rod at a distance x, L upon N from the midpoint of the rod, see figure, then the rod and the string revolve together around the point O, with the rod remaining aligned with the string. In such case, the value of N is. So basic figure is given to us. So we are having a string. So this is a string and it is of length L, and we have a rod which is also of length L. Impulse P is applied at a distance L by N away from the, so this is the midpoint, and from the midpoint at a distance of x, and midpoint of the rod, and this x is given as L by N. So we have to find out the value of N. Okay. So let us say this point O is having a coordinate O, 0, 0, and the string is of length L. So therefore let us suppose this is point A and the other point is our B. Then the coordinate of A will be our L, 0, and the coordinate of B will be equal to 2L, 0. So let's first of all define the geometry and coordinates. Geometry and coordinates. So we have our pivot point O, which is our origin. So we are going to have 0, 0. Next is our point A, which is our L, 0, and we have then our point B, which is our 2L, 0. Okay. And let us call this center of rod as point C. Okay, let me draw this figure on the larger scale. So this is A, B, and string, this point is our O. So this is 0, 0, this is L, 0, and this is 2L, 0. Okay. And let us call this a midpoint of this rod, that is our C. So we can say midpoint of rod, which is basically center of mass. So we can say rod's center of mass for rod, let us call this as XC. Then this XC will be equal to, this distance is our L and this distance is our L by 2. So this comes as L plus L by 2, giving us 3L by 2. Therefore our C is going to have a coordinates that is 3L by 2, 0. And we are applying an impulse at point D. So let us suppose this is the point D where impulse is being applied, and from C this distance is given as x, and that is our L by n. So we have this distance is our x. So we can say that impulse is applied at point D at a distance x is equal to L by n from point C. Therefore, we can say that our x of D will be equal to L by 2 plus L by n, which gives us L we can take common, so this comes as a 3 by 2 plus 1 by n. And so we found out all the distances, and we have to remember that all the distances are with respect to this origin O. Okay, now let us move on the linear impulse as well as the momentum. Linear impulse and momentum. So the linear momentum, let me say this is our rod, point A, point B, and linear momentum is applied upward, that is our, impulse is applied upward, let us call this impulse P, okay, and its direction will be our plus J. This is our x and this is our y. So we can see impulse P is applied perpendicular to the rod. Plus J direction. So the center of mass gains a velocity let us call this as VCM. So the center of mass is our C and it gains a velocity of VCM, and this is going to rotate about point O, which is somewhere here. So it is going to rotate in this direction, and angular velocity is suppose omega. Gains a velocity VCM and rotates about point O and rotates about point O with angular velocity omega. So we can write that the linear impulse changes the momentum of the rod. Linear impulse changes momentum of the rod. Which means that the integral of our force for small time dt will be equal to change in the momentum, and which is equal to over m velocity of center of mass minus 0, because initially it was at rest, and this can be written as momentum p in j unit direction will be equal to m velocity of center of mass. And we know that our center of mass is at a distance 3L by 2 from O, because the rotation, we have to remember, is with respect to the origin. So we can say that center of mass C is at a distance, let us call this as RCM, which is equal to 3L by 2 from O. Therefore, we can say that velocity of center of mass will be equal to omega 3L by 2. L by 2. Okay. And with respect to direction, we can say that if omega is counterclockwise, that is k unit vector. Therefore, our VCM, one second, this is, because it is moving in the horizontal plane, not on the vertical plane. Okay. And our momentum, that is our P, we can say our momentum, which is our P, will be equal to mass into velocity center of mass, which comes as our m omega 3L by 2. And from here we can write that our omega will be equal to 2 times momentum P divided by 3ml. And we know that momentum is applied at a distance of we know that impulse P, not momentum. Impulse P is applied at xt, which is equal to 3L by 2 plus L by N. Therefore, angular impulse about O. Angular impulse about O is our tau is equal to R cross F, or we can further write it as integration tau dt is equal to our R cross F dt, and this R we can write as RD because the point is D, and therefore we can say that our angular impulse is our RD cross, this is nothing but a momentum, that is our P. This comes as our RD is our nothing but our xt. So this is our 3L divided by 2 and plus, and we have this as cross P, and okay, we are only interested in magnitude. Therefore, we can say that this delta L will be equal to L upon 2 plus L by N times P. Now the angular momentum about O. Angular momentum about O. So we can find out its moment of inertia about center of mass. So we can say moment of inertia of rod about center of mass, that is of ICM, will be equal to 1 upon 12 ml square, and distance, you can say that distance from O to center of mass, because we are going to use parallel axis theorem, so that will be D is equal to 3L upon 2. So we can say that our parallel axis theorem, and we can write it as that moment of inertia about O will be equal to moment of inertia about center of mass plus mass and the distance square. So we get this as 1 upon 12 ml square plus m 3L upon 2 whole square. and we get this IO is equal to 7/3 ml square. Therefore, angular momentum which is our L will be equal to our I naught multiplied by omega, and this comes as our 7 omega L square upon 3. 7 omega m also, and we can equate our angular momentum, angular impulse to change in angular momentum. So you can see equating angular impulse to change in angular momentum. So we get this as our 3L by 2 plus L by N times P is equal to 7 omega L square by 3 times M. And from here we can write that our omega will be equal to, this comes as 7 ml, this L square cancels out, and in the numerator we get this as 3 times 3 by 2 plus 1 by n times p, and we have two expressions for omega. One is this one and another one is our this one. So we equate them. So this will be equal to 2p, and we have this as 3ml, and this p, ml and ml cancels out. So we get that our 2 by 3 is equal to, this will be our 7 3 times 3 by 2 plus 1 by n. And now it is quite simple. We are going to solve it, and this will be giving us value of n is equal to 18. So value of n was 18. The concept here is comparatively easy. Only thing is that it is quite lengthy to solve. And this completes all the questions from the year 2023 Mains Advanced, and also the questions of year 2024 Advanced. Thank you.